Class. Okay, so we're going to talk about electromagnetic waves. So I drew an electromagnetic wave here, where I use blue for the electric field, and red for the magnetic field. Okay, now we're considering a wave that is propagating to the right. So we've got velocity to the right, or the x direction. Now we have three vectors here: the electric field, magnetic field, and velocity, and they're all perpendicular to each other. So the way I drew it, the electric field is in the y direction. So it oscillates. Like this picture I drew would just be like what it would look like at one moment in time. So if this board is the xy plane, we could describe the electric field with like a, as a sine wave. And so, if you look at moving down the wave, the electric field points up or down, it oscillates up and down. And so it can be in the plus or minus y direction, depending on what part of the wave you're looking at. So this is one way to look at a wave, just like this snapshot kind of picture of what it looks like. Another way is you can imagine you're standing here, and this wave passes you. And if you plot the electric field as a function of time, it would look just like this. It's different units, but it would also be described by a sine wave if you're just at one point observing the electric field. Okay, now the magnetic field is in the z direction. So if the board is the xy plane, z is coming out of the board or going into it. Positive z is coming out of the board. So remember, right-hand rule. You put your fingers in the x direction, curl towards y. By convention, z is out of the board. So, like here it's out of the board, and this portion it's into the board. Kind of hard to draw the magnetic field because it's perpendicular to the board. But, then the velocity is in the x direction. So again, we're forced to look at three dimensions here. It's not as bad as it seems, though, which I'll get to in a minute. But these three vectors are all perpendicular to each other. Now, we can say a little bit more about the relation between the electric and magnetic fields, just direction-wise. What I drew is a wave propagating to the right. However, I could erase this, and just looking at the picture, you can actually tell which way this wave is moving. Maybe not now, but once I tell you how. So the way I drew it, this portion here, the magnetic field is coming out of the board. Let's do this. And here it's going into the board, here it's going out of the board, there it's going into the board. So it's not obvious from the picture, that's what it's doing. And if you look at this first kind of region here, where the electric field is in the positive y, and the magnetic field isn't coming out of the board, so it's in the positive z direction. If you put your fingers in the direction of the electric field, in a way that you curl your fingers in the direction of the magnetic field, your thumb points in the direction of the velocity. So in this bubble, E, curl your fingers towards B, thumb points to the right. Now if you look at this section here, fingers point down, but now the magnetic field is into the board, so again, if you do that again, it still points to the right. So whatever portion you do this, the rule, we can actually write this as an actual equation if you're familiar with this cross products. So one of the ways to multiply vectors. So again, you don't have to know what cross products are in this class, but if you do know, you can get the direction from the right-hand rule. And it's proportional to v, the velocity. it'll point in that direction. Okay, so just from looking at the directions of the electric and magnetic fields, we can tell which way the wave is moving. Now, soon we're going to see that there's another relation between the electric and magnetic fields. We can also look at the magnitudes, and we're going to see how the magnitudes of the electric and magnetic fields are related. And because there is a relation there, we can describe a wave just by drawing the electric field. So if I were to give you a wave, let me draw a new coordinate system. Let's say I gave you a wave that looked like this, where the electric field looked like this. So that's the electric field. And if I told you this wave was moving to the right, you could see what direction the magnetic field is just from using this right-hand rule. Like here, it's coming out of the board. So again, this E, curl your fingers in the direction of B, thumb points in the velocity. So you have to set it up like this, and then your fingers would curl out of the board here. Over here, just remember your thumb always points in the direction of velocity. And so you can always see what direction the magnetic field is from the right-hand rule. And again, we're going to see a relation between the magnitudes as well. So if I just give you the electric field, then you know everything about this particular wave. You know both the direction and magnitude of the magnetic field as well. So that makes describing electromagnetic waves a little bit easier. Okay, so let's get to that. So I'm going to erase this picture. We don't really need it anymore. And I wrote over here, when we talked about energy density stored in electric and magnetic fields. And the main reason we even figured that out, we did that by charging a capacitor, seeing how much energy it took to charge it, and said that energy is stored in the electric field. And so by looking at a parallel plate capacitor, we were able to calculate the energy density. And similarly, from a solenoid, we could calculate the energy density stored in a magnetic field. Now, light consists of both electric and magnetic fields. So I'm going to draw this wave again, but I'll just draw the electric field. Now, there are a couple important relations because we're talking about a wave here. So first off, if you look at one peak to the next, this is the wavelength of the wave, going from one peak to the next. And just, typical for waves, the speed of a wave is a frequency times the wavelength. And, normally we use V for velocity, but C is kind of a special symbol just for the speed of light, which has numerically around 3 times 10 to the 8th power meters per second. It's actually very close to that. It's 299. Not sure if I'm getting these mixed up or not, but I think it's 299,792,458 meters per second, and that's an exact value. So again, if you go to, let's see, 5 decimal places, or if you stop at 4 significant figures, you'd round this up to 3 times 10 to the 8. So, this is a good enough number for anything we're going to do in this class. You wouldn't use the exact value unless you're doing something with extreme precision, way more than we need. Okay, now let's do a quick calculation. Let's say we have light with a wavelength, let's say ordinary light. Let's say the wavelength is 510 nanometers. which is somewhere in the middle of the spectrum, probably like green or yellow or something. Not sure exactly what color that would be, but somewhere in the middle of the spectrum. Let's find the frequency of this light. So the frequency, that would be the speed over the wavelength. So we have 3 times 10 to the 8th meters per second. And then the wavelength is 510 nanometers. Remember, nano is 10 to the minus 9. So we can put that on top, 10 to the positive 10 to the 9 on top. And what I'm going to do is I'm going to say 3,000 on top. So here we have 3 times 10 to the 17th power. But I'm going to say 3,000 times 10 to the 14th power. Same thing. But this is just writing it in scientific notation. So it's actually 3 times 10 to the 17, but again, 3,000 times 10 to the 14th is 3 times 10 to the 17th. I'm going to even get rid of this. And again, this number is around 6, maybe 5.9. So, meters cancel out. We have units inverse second. That would be hertz. So the frequency would be around, let's just say around 6 times 10 to the 14th hertz. So that's, let's see, what is that? 60,000 billion cycles per second. So if you were to look at this wave for 1 second, yeah, this is how many cycles you would see. So if you were to actually look at this wave and look at the electric field, it's going up and down, but it is happening so fast. If you even look at it for a nanosecond, you're going to see literally 60,000 cycles. And so we really only concern ourselves with average values when we're talking about these properties of waves, particularly when we have things like visible light. These are oscillating so quickly, you're never going to detect that up and down motion directly. So what we're going to talk about is like the energy delivered by a wave. We don't want to see that going up and down. It's not going to matter at all. It happens way too quickly for us to worry about that. But yeah, typically visible light is measured in nanometers, and the frequency is around 10 to the 14th hertz, which is extremely rapid. So again, because we only concern ourselves with average values, let's say this is the peak electric field. Let's say EM for maximum electric field. I'm just going to write this down. So the RMS average is just the maximum value divided by the square root of 2. So again, if you take the average value of the electric field, you're going to get 0 because it's perfectly symmetric function. We're describing this as a sine wave. So again, average value is 0. And so we've done the RMS enough that we can just say this is how we take averages. We square it, take the average, and then the square root. Okay. And the same thing with the magnetic field. Might as well write that down. Okay, so these are the kind of average values, which is usually what we care about. But if we look at a beam of light, let's say we have a ray of light, like you can create a narrow beam, letting light travel through a narrow pinhole opening, or you could use a laser. But yeah, like say we have a beam of light, and so it occupies a certain volume. I don't know how much energy is in this. Well, you can talk about the energy density. It has electric and magnetic fields. Okay. Now, we're going to make this assumption, which is perfectly reasonable one to make, that because it's oscillating, these electric and magnetic fields, you know, remember the graph, they overlap. They have the exact same frequency. Right, they're both 0 at the same time, and they both reach their peak values at the same time. So so if you like watch the, let's say you're standing here and you watch it go by, yeah, we're just going to state that the average energy stored in the electric field is the same as what's stored in the magnetic field. So they're just changing back and forth. It's the changing electric fields that create the magnetic fields and the changing magnetic fields that create the electric fields. And the energy is stored evenly between them. And so basically these two terms are equal to each other. So we can state the energy density in two different ways, other than, you know, the basic. See, if we say that this term is equal to this term, if we just replace the second term with the first one, we add them up and just get rid of that factor of 1/2. Similarly, we can replace the first term with the second and get rid of the 1/2 that way as well. Okay, and now what I'm going to do, let's just based on this idea that it's oscillating between the two very rapidly, but the energy is stored equally between them. Just by looking at we have this equation here. We can say that E squared is equal to 1 over mu naught epsilon naught B squared. And if we take the square root, you can say the electric field, remember I mentioned earlier that there's a relation between the magnitudes of the electric and magnetic fields, and here it is. So the electric field is 1 over the square root mu naught epsilon naught times the magnitude of the magnetic field. Now it was Maxwell who first came across this calculation here. Like, what is this number? 1 over mu naught epsilon naught. And historically, I should point out that the SI system did not exist in Maxwell's time. So he was using a completely different set of units. But what he did is equivalent to this. And if you calculate this, you will discover that it is just the speed of light. So again, you can just do that calculation, and numerically and unit-wise, you will get 3 times 10 to the 8th power meters per second. So, ultimately, that's how mu was defined to be a precise value. We have epsilon naught, which is kind of an experimentally determined number, and we can define u so that this gives us that the speed of light. But previously, mu naught was an experimentally determined number as well. And so this was something that was very shocking to Maxwell when he discovered this. Because, again, these, epsilon naught, this came from, Coulomb's law. Just the attraction between these charges. And mu naught came about by looking at, how strong a magnetic field is next to a wire. You don't normally associate these things with light. But, Maxwell discovered that connection there. Okay. I think that's actually all we need for this. We're looking at energy density, which we can write in 3 different ways. This is, the basic here. Basically we have these 2 terms we add up. But just that fundamental assumption that the energy is stored equally between the electric and magnetic fields allows us to write it in these alternative ways. And it also leads to this result I'll write the final result down here, that the electric field is equal to the speed of light times the magnetic field. So I think that's, that's all we need for this topic, but kind of a short one. But next, we're going to talk about the intensity of light. And again, light waves are fairly complicated because it involves two vectors, electric fields and magnetic fields. But because the way they're related, we can just describe the intensity of a wave just by looking at the electric field. If you know what direction your wave is moving, if you see the electric field, you immediately know the magnetic field as well, both its magnitude and direction. So just to summarize, energy density. This normal relation, the speed of a wave is frequency times the wavelength. And the relation between the electric and magnetic fields is magnitude and also distance. We have fingers in the direction of the electric field, curl towards the magnetic field, thumb points in the direction of the velocity of the wave. So that's what we need to know just for this lecture, but then we're going to talk about intensity of a wave, and so we'll revisit this. That'll be all for now, though.